Hello, in this video we're going to look at how to determine what your conclusion for a hypothesis test should be if you're just given the p-value. And when you're given the p-value like this, you can assume conditions are met, even if that's not stated in the problem. Alright, so here's an example. A research facility is testing a new model for predicting hurricane paths to determine if it is better than the old model. And the old model was able to accurately predict hurricane paths 37% of the time. The test of the new model, which met all conditions, resulted in a p-value of 45%. Should the research facility adopt the new model or remain with the old model? Alright, so first let me just kind of clarify, there's a lot of p's going around. So just let me clarify, there's three p's here. There's p hat, which is your sample proportion, the proportion of objects or people in a sample that have the trait. Then there's p, which is the proportion of the people or objects in the population that have the trait. And the p-value is something completely different. It's the probability of getting the sample you got, or one that's even less likely, assuming the null is true. So all of them are measured as percents, so that can be a bit confusing. Now, in this case, all we're given is the p-value. We are not given p hat. We are given p because that's the 37%. So your trait then is whether you accurately predict a path or not, right? That's the trait. And the population are the predictions themselves, predicting the hurricane paths. That's actually your population. So you may predict and it may be wrong. You may predict, it may be right. All right, so then the p is 37, and then this is our p-value. It's 47%. All right, so given all this, what you would normally start to write is a hypothesis. And normally what you do is you'd say, well, here I'll write my null and my alternative, right? And you'll say p equals 0.37, or is p better than 0.37 or greater than 0.37? So again, translating this is the proportion of predictions, which are predictions of the hurricane path, that are accurate for the new model is only 37%, or the predictions for the path of the hurricanes with the new model is better or higher than the 37%. Now, normally you do a bunch of work, and all the work that you do is to actually get the p-value. And it's the p-value that you need to be able to write your conclusion. So you compare your p-value to your significant level, alpha. Right? And since they didn't give us one, we're going to assume 5%. But they did give us the p-value. That's 45%. That's astronomical. It's an extremely high p-value. So basically, since your p-value is much, much higher than your significance level, you do not, in this essence, you really super do not reject the null. You do not reject the null. So the null could be true. So then you'd say, that's not, the alternative is not likely to be true. So you'd say there is not enough evidence that the proportion of accurate hurricane path predictions with the new model is better or greater than the old model's 37%. So what that means is you really shouldn't adopt the new one, because then you'd have to basically reprogram probably computers, and it costs a lot of money. It's no better. Okay, so that's one way of obtaining this result, of knowing what your conclusion should be. Here's another way. Again, when you're writing these, you're still going to have work with the null and the alternative, right? And you'd say P equal to 0.37 versus P is greater than 0.37. Now, what you'll notice is, remember, the direction of the alternative, when it's written in a sentence format like this, the proportion of accurate hurricane predictions of the new path is greater than 37%. That's a sentence. When it's written this way, the direction of the inequality tells you which way to shade. So you have two possibilities. Where did P hat land relative to the truth P? Well, we know generally when we take samples, they almost never land on the truth. Sometimes they do, but really there's a lot of sampling variability. So let's assume to the left of P, the mean. So if P hat landed to the left of the mean P, then we're told we have to shade to the right. And what we know or see right away is that half the curve, this is more than half the curve, and half the curve is already 50%, and then you'd have more than 50%. But we know the p-value, given our problem, is 45%. So we know this particular scenario is not possible. So the only other thing that could happen is that relative to the mean, sorry, that should be more in the middle, P hat must have landed to the right because the p-value is to the right of the mean because the p-value is less than 50%, and so that makes sense, less than half the curve. But we can do even better than this. We know from the empirical rule that when we go out one standard deviation in both directions, we capture 68%, right? Meaning 34% on either side of the mean. We capture 34% of the sample proportions. Well, in this case then, since half the curve is 50%, then we can say this piece right here is 50 minus 34, or 16%. So we know already that this here is 16%. But remember, our p-value was 45%. So what we really have is we know that we have not only all, when we shaded to the right, we have all of this plus quite a bit more. And in fact, we know 45% is really so close to what? 50%. It's really only 5% away from the mean. Right? We know that. So what we know then is that our sample proportion landed so close, but so close to the mean. It's well within one standard deviation. It's really close to the mean, actually. It's close to 0 standard deviations. So what that means is we got our model predicted what was going to happen, meaning the distribution of sample proportions. We got a sample proportion that was incredibly reasonable to get. Therefore, our null could be true. And if the null could be true, then what's not likely to be true? The alternative. So we would come up with the same conclusion. This is more of a visual way, and the other way was more of a written way. Thanks so much for listening.